Hello everyone, my name is Wanling Gao from Institute of Computing Technology, Chinese Academy of Science. My topic title is the IoTs, edges, data centers, and humans in the loop as a computer. So let's first take a look at the landscape of the warehouse scale computers. The concept is the data center as a computer that non-stop serves user requests. And as a typical data center applications, internet services mainly serve concurrent and independent user requests. And the independency exists not only in the same person's different requests, but also in different persons' requests. However, this situation changes for the emerging and future applications like medical emergency management and autonomous driving, and they pose different requirements and challenges. We conclude 3 unique requirements for these applications. The first one is the humans in the loop. We abstract 5 steps for the execution loop, including observe on IoT device, process the data, make decisions, and human decide whether the decision is okay and take actions. Moreover, different from the internet services that are mainly business critical tasks, the future and emerging applications are safety critical and mission critical tasks. Here, safety critical means the system's failure may result in injury, loss of life, or serious environmental challenge. And mission critical means the system failure may fail some goal-directed activity. So in this condition, the results may have the irreversible effects. Since the system considers human as the essential parts, there are 3 kinds of human in the loop, including the reliable human in the loop, unreliable human in the loop, and collaborative human in the loop. Among these 3 conditions, only the reliable human in the loop is reversible, and the other 2 is irreversible effects. And in other conditions, like the system makes a solo decision, we think it is the no human in the loop, and the results is irreversible. And the second unique requirements is dependencies. We conclude 2 kinds of dependencies. The first one is the internal dependency, indicates the dependencies between agent execution loops. And the second one is the external dependency, indicates the dependency between actions or decisions triggered by IoTs, edges, data centers, or humans in the loop. And it has the diverse execution paths. From the perspective of the task scheduling, the actions or the processing or the decision may be on cloud or edge or IoT device. And from the perspective of the execution loop, the execution path is diverse. It may go through the observe, process, and turn back to observe, and the or observe process, and then there's no need to for the decision and go directly to the acts, or the human is in the loop or other human, no human in the loop. So the execution path is diverse. And the third unique requirements is the metric constraints. The system needs to meet the accuracy metric and performance goal, and different cases like the average case, best case, and the worst case. And we think the accuracy is the precondition. They need to assure the nearly 100% accuracy during the whole process, including the predicting, interpreting, and take actions. And the performance is another important metric. The applications care, for example, the many applications care about the low tail latency and within several milliseconds. These slides show the comparison of the emerging and the future application to the traditional applications. We take two metrics as an example. The first is the quantity requirements, for example, the accuracy, and the worst case performance requirements, which is the tail latency. We find that the emerging and the future applications have a higher demands compared to the traditional applications. They require nearly 100% accuracy constraints and extremely low tail latency requirements. Next, I will use two examples to illustrate the three requirements. The first one is the medical emergency management. It is a safety critical application, and it has reversible effects. Since the doctor is in the loop, we think doctor is reliable human in the loop, and it goes through the observe, fields, recommend, train, and human execution loops. And we think this application has strong internal dependency because the person's medical records will impact the follow-up recommendation and the decision. And it has the weak external dependency because an updated training model based on similar disease record will improve the treatment method and further impact other person's treatment. But we think that is long time. It takes long time, so it has weak external dependency. And another example is the autonomous driving. We think it is a safety critical application, and it has irreversible effects. We think it is the no human in the loop. Since considering the human's reaction time and the emergency situation, we think human can have low time to take a correct react on the emergency. And different with the above application, it has strong internal dependencies because the current status and action of a car will impact its subsequent computations and actions. Also, it has strong external dependencies because a self-driving car status and action would affect the behaviors of the other vehicles. Next, I will introduce the motivation. Why we need a new computer system. So let's take a look at the simple application. This example is a simplified smart home application, and we set the percentile latency is 50 milliseconds. The queries includes the 95% queries are only simple reporting status and sending heartbeat packets, and only 5% of user requests and need to access the Redis database. And there are three kinds of network stacks: the colo TCP, MTCP, and the LNCS network stack proposed by Dr. Zhang. And the paper find that for one machine, the collections is up to the concurrent collections is up to about 10 million, and considering the tens of billions of IoT device, we need at least 1,000 machines for this simple application. So the question is, the future and emerging applications requires extremely lower response time, and they have longer communication links, more complex computation and interaction patterns, and they have applications irreversible effects, and they have different processing abilities on the IoT or edge or data center. So we conclude that these applications demand resource that's several orders of magnitude beyond the reach of the state of the practice systems. And another reason is that we find that even with the same infrastructure, the gap may achieve dozens or even hundreds of times, considering the total response time, considering the task complexity, device processing capability, and available resources, and so on. So we think we need a new computer system. And our goal is to build a new computer system that reconstructs IoTs, edges, data centers, humans in the loop as a computer, using a structural manner with full-fledged functions. We can support autonomic resource discovery, management, programming, and the workload scheduling, and supports the collaboration between the software, hardware, and the human components. And this slide shows the concept viewpoints of the new computer system. We aim to collect the physical world and the digital world, and collect the IoTs, edges, data center, and the humans in the loop as a computer. Next, I will illustrate the challenges. The first challenge is the organization and the management challenges. Since the system is geographically distributed, so the problem is how to discover the resource and assemble them into a computer system, how to achieve unified programming, how to manage these resources, and schedule the optimal execution paths. The second challenge is the collaboration challenges between the software, hardware, and the people components. Since many systems consider the human in the loop as the external and unpredictable elements. If we have human in the loop, which one should we choose? The system decision or the human's decision? How we support the system and the human collaboration? What's the system's responsibility and what's the human's responsibility? And if we have no humans in the loop, how to verify and validate the system's decision? And in this condition, what's the human's responsibility? The third challenge is the irreversible effect challenges. So the question is how to trace the impact of different attributing factors or even achieve interpretability for the best case, average case, and the worst case conditions, spanning the design, implementation, verification, and validation stages. The fourth challenge is the ecosystem war challenge. Since the data center ecosystem, IoT ecosystem, and the edge ecosystem is gradually mature, and the war has been matured, and they have different scopes and boundaries. They have distinct guidelines and targets, considering the energy consumption, chip area, or performance. So how could we break this ecosystem war and collaborate this together? Is a huge important but challenging problem. The fifth challenge is the effective evaluation challenges. The first one is the benchmark challenges. So the question is how to evaluate and optimize the systems. From the perspective of the applications, it has extremely complex applications, including hundreds of thousands of lines of code, and have confidential issues. So how can we abstract the real-world applications and provide the benchmarks for evaluation? And from the perspective of the platforms, large-scale clusters are hard to obtain, and they incur huge deployments and maintenance costs. So how we provide or obtain the platform for the evaluation is a big problem. And the second one is the simulation and the validation problems. Simulators are widely used for system and architecture evaluation. However, for the emerging and the future applications, they are extremely complex and diverse, and they have no unified interface for IoT edge and data center. And simulation accuracy is an important metric for the simulation. So how to simulate and validate the system behavior is another challenge. And next, I will introduce our solution. Inspired by the Gordon Moore, who proposed to build large systems out of small functions, we propose a FuncNet methodology and architecture. FuncNet, we provide, we think the FuncNet has four kinds of FuncNets. From the chip level, it is the chipnets, and from the hardware management level is the hardware nets. And from the environment management level is the ENV nets, and from the service level is the server nets. So each net is a well-defined and evolvable functionality, and they are reusable in different contexts. They are independently tested and verified before integrating. They can be independently deployable, and they can interoperate through interface or interconnection. And these slides show our architectural overview. We first provide benchmarks and provide tools to support the FuncNet's design, and we explore the kernel technologies for each FuncNet, from the chip nets, hardware nets, environment nets, and the server net level. We explore the technologies and provide the implementations. Next, I will introduce our plan. We make a 5-year plan. First, we will provide a methodology and the benchmarks and the standards. Then we provide the design and technologies, the scenario simulator for the to solve the platform challenges, and we provide system design tools and the full stack optimization tools. Then we provide the open source implementation of 4 kinds of FuncNets, and then we provide an open source computer system. So finally, I will make a conclusion. We launched an open source computer initiative aiming to reconstruct the IoTs, edges, data centers, and networks of the computer. And we conclude the 3 unique requirements of the emerging and future applications. They are human in the loop dependency and metric constraints. And we think they demand resources that several orders of magnitude beyond the reach of the state-of-the-practice systems. And we propose the FuncNet methodology and architecture to solve this problem. So that's my talk. Thank you very much.